Welcome back, everyone. It's day 7. I'm wearing a hat. This is not, I didn't just start recording from day 6. It didn't happen. This is a new day. It's a new day 6. Let's get into it, okay? Day 7, we're going to take a look at the problem together. As always, we are going to go into Ellie here. Hello. Hit compile. And that is going to allow us to write code on the left, see it on the right, and then we're going to work through the problem together, start to finish. I'll be talking through me thinking about it, and you'll get to see me be confused for 30 minutes or more. We'll see. But yeah, let's dive into day 7. If we do this, this officially marks 1 week Advent code, and then I can relax and I can retire and go back into my cave for another 12 months. Let's get into it. Let's see how it goes. All right, day 7, bridge repair. The historians take you to a familiar rope bridge over a river in the middle of a jungle. The chief isn't on this side of the bridge, though. Maybe he's on the other side. When you go to cross the bridge, you notice a group of engineers trying to repair it. Apparently, it breaks pretty frequently. You won't be able to cross it until it's fixed. You ask how long it'll take. The engineers tell you that it only needs final calibrations. But some young elephants were playing nearby and stole all the operators from their calibration equations. They could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations, which is our puzzle input. So I'm going to steal that. All right, for example, 190, 10, 19, 32, 67. Each line represents a single equation. The test value appears before the colon on each line. It is your job to determine whether the remaining numbers can be combined with operators to produce the test value. Operators are always evaluated left to right, not according to precedence rules. Furthermore, numbers in the equations cannot be rearranged. Glancing into the jungle, you can see elephants holding 2 different types of operators, add and multiply. Only 3 of the above equations can be made true by inserting operations. 190, 10, 19 looks like plus, yeah, it gives us 29, but the times would give us 190. 3267 has 2 positions for the operators. One of the 4 possible configurations of the operations. Wait, what? Configurations of the operators 2 cause the right side to match the test value. 81 plus 40 and 81 times 40. Wow, they both equal 3267. That's crazy. I didn't know math could do that. And then 292 can be solved in exactly 1 way. So they need the total calibration result, which the sum of the test values and the equations that could possibly be true. In the above example, the sum of the test values for the 3 equations is 37, 49, 190, 32, 67. So when we add these up, it looks like it's not double counting this, even though it had 2 possible variations. So my guess is part 1 is this, and then my guess is part 2 is you have to keep track of how many different ways it works instead of leaving early. So I don't think this is going to be too horrible. What we need to do is basically parse this so that we have a list of numbers, and then we have kind of the solution that we're looking for. And then once we do that, I think we just kind of go through all the permutations of plus and times and see if see if we can pull it off. I wonder what's gonna happen. I think it's gonna, they're gonna do something tricky in part 2, but it ain't gonna be tricky in part 1. That's my vibe. Let's dive into it. So we've got the input. We got a list of string lines. This looks good. What I'm gonna do is I'm gonna say we're gonna turn these all into equations. So to equation, I'm just gonna take in a single line, and maybe it'll give us back equation. So let's create an equation type real quick. This is going to be the answer, which is going to be an int, and then it's going to be the parts, which is going to be a list of ints. So the way I'm going to go about this is for each line that we have, I'm going to do string.split on colon space. And if that gives me a left side and a right side and nothing else, then I'm going to do string.words on the right. So I'll do just actually, I think we want maybe.map. Maybe.map to equation. So the left is still a string. This is the reason I'm doing all this maybe stuff. So I'm getting ahead of the curve. What we want to do is we want to say string.toInt. Not every piece of text can become a number, so we need to handle the edge case there with that. With the maybe, toInt returns a maybe. And then right will give us 10 as a string and 19 as a string. So we also want to do a list.filter map. I don't think that's a map 2 though. I think what we want to do is, well, whatever. I'll just be lazy. I'll throw a just in here, and then the equations will work out. Okay, so that's if we did have a left string and a right string. Left string and a right string. What we want to do next is we want to say in any other case, this is just bad input, so we're just going to return nothing in those cases. So I'm going to do this, and then hopefully we get a list of equations here. I guess you have to use the line variable if you're gonna be doing that. All right, so we've got the answer 190, and we have the parts, and they're all broken up as integers, which is good. So this is going to allow us to kind of insert stuff together. So what I want to do is I want to kind of work left to right and try add, try multiply, try all these different operations. So I want to see the puzzle input and see if I should be scared. Yeah, I should be scared. Okay. So what we need to do is we need to basically try 10 plus 19, and then we try 10 times 19. And if we run out of options, run out of different permutations, then we're done. So let's figure this out. I think with the operations, if we kind of give them an order, we can try each of them. I think there's a list extra library that's going to help us with the permutations. So let's try that out. I just want to kind of play around with that a little bit and see. I'm going to call this equations. List of equations. And we're going to leave that as is because that's good. What I want to do is I want to see what happens if I say add. How am I going to do this? Remember when I said this is going to be easy? All right, what I want to do is create a bunch of permutations of all this stuff, I think. So I got to try every combination of add, multiply, whatever. I could make all those permutations as lists up front and then kind of try each. I'm thinking like binary, like 0, 1, like, sorry. That doesn't make sense, what I'm saying. What I'm thinking is like, each slot. So, all right, so let me just kind of talk through this. I've got 10 plus 19. I got to try this. Then I want to try 10 times 19, and then I'm done. So when it comes to all the permutations, I had plus, I had times. That was with 2 numbers. When it comes to dealing with 3 numbers, it could be plus plus, it could be plus times, it could be times plus, it could be times times. And the reason I was able to think about that is because this is 2 to the power of 1, this is 2 to the power of 2. However many gaps I have, that's how many combinations I can have, because there's 2 basically things I can switch between. And so I'm trying to figure out how to do a thing so that I can kind of quickly test everything. And I'm wondering if The crazy idea I had was you take the number of gaps. So you take the length of the words. So like I take 2 minus 1. That's the exponent. And then I loop from 0 to 2 to that exponent minus 1. And that'll tell me like the binary, like 1001, whatever. All that stuff. If you treat the pluses as zeros and this is crazy. I think I'm losing it on day 7. But the idea is this is the mathematical equivalent of 0, and this is 1, and this is 2, and this is 3. So if you treat the pluses like zeros, you can basically translate these to numbers. And then what I can do is I can work for each equation. I take the length. So the length of this is 2. I say I want the range starting at 0. I want to go from 0 to 2 to the power of a list.length. I'll put my equation here. This is like my upper bound, I guess. So like, this is how I know what I'm done. So I take the equation, and then I'll say get the length of the equation parts, subtract 1 from that, raise 2 to the power of that, and then subtract 1 because we're going off of indices. So I think 2 to the power of 1 is 2. So 2 minus 1 is this is the final number. This is basically where I stop. So I could say like upper bound, I could say like don't go past. But the idea is this represents how much space I need to simulate through. And then what I would do is I would use the position. I would use the position here to determine like for like slot I don't know, this is crazy. For A and B, I would know that like if A is 0, do a plus in between the first 2 numbers. If B is 0, we're going to do a plus, and then I'll try 81 plus 40 plus 27, and if that equals this. I don't know why I'm doing it this crazy way, but it's exciting to me. So I'm going to just do this, and we'll see if it was horrible. So what I want to do is I want to take the equations. I'm going to kind of move this here. I don't know why I'm thinking the way I'm thinking, but we'll go back to the equations. Oh. Cool. And what we can do is we can actually just do the upper bound. We can say equation, upper bounds, parts.length. So I'm going to try to basically filter this list of equations down next. So we're going to say list.filter can be mathed. So it can be mathed. I'll take an equation, and it's going to turn true if we're able to add some numbers of plus and times to get this thing to work. So what I'm going to do is I'm going to get that upper bound. I'm going to say upper bound equals 2 upper bound. The equation, I'm going to rename that function we made above to match this. And so what we want to do, this is now going to be an integer. So we want to start at 0. And then I'm going to do some bit stuff, bitwise, core bitwise. We're going to import the bitwise module, and this should allow me to I think this is how do I think I like and it with let me try something. I'm going to try a bitwise. I'm going to just do some math stuff to make sure that I know how to like read these values. I went to school for computer engineering, and it might be showing right now. This is a very hardware person way of solving a problem. This is a part of my brain I haven't really gotten to scratch that much making the button round in my day job as a front-end developer. But I think that Advent Code is a really good outlet for this kind of crazy energy that I would never put in a production code base. But it's fun. This is what puzzles are for. It's about being a little psychopath every now and then. Let me see. So what I want to do is I just want to test. So if this all returns false, then we get an empty list, and then the answer is, I guess what this is. This should be a filter map, because what we're really trying to return with our main is the like the answer for each. So this would be like equation dot answer. So if we found out that it could be mathed, we would basically just return the thing, and then we'd call like a list.sum at the end. So like this is how we'd actually solve the problem. But what's missing here, there's a to-do, which is check if plus can work. So this is like the big thing that's missing from CanMath. I'm gonna move this back up to the top, move all the way up to the top. What I want to do is I want to actually play around with this to make sure that I know how to read if there's a 1 or 0 here. So for example, if I have a 3 and I AND it with 2, that should give me a 2. I'm trying to figure out, I forget how to do things. Solve. So that should give me an integer when that's done, right? Okay, great. All right, so let's have some fun. Let's do a bitwise AND. If I give 3 and 2, I should get 2 back. If I do 3 and 1, I should get 1 back. And if I do 2 and 1, I should get 0. Okay. So basically, if I map the plus to a binary value, this is stupid. This is not going to scale when I have... This is dumb. The way I'm doing this is dumb. I need like trinary later, and I don't think bitwise is gonna... The math's not gonna map. Let me see if this is stupid. I really hope part 2 doesn't add another operators, because if it does, yikes, I gotta do trinary. All right, so here's what I'm gonna do. Plus bit equals, it's basically the binary for 1. Elm doesn't have a thing for this. So I'm just gonna translate this here. But I'm just gonna add a little comment here. This represents the first bit position. This represents the second bit position. Actually, no, this represents... So if times represents a 0, oh no, this works fine. Yeah, because it's whatever. This, yeah, the plus. No, this isn't right. Plus value, yeah, plus. These are called masks. I don't know. Okay, so we have the plus mask and the times mask. We're gonna loop through all these numbers. All right. We're gonna say can be mathed. That's good. What I'm gonna do is I'm gonna say can be mathed help. We're gonna give it an initial value. We're gonna give it an upper bound. Like that. Value. If value is greater than or equal to the upper bound, return false. Oh, I need the equation too. If can be mathed, then we do this. This to do moves over here. Otherwise, we discard the answer. So now this is where the meat of our logic is going to go. I'm going to just adjust this quick. Hopefully the lighting's okay. Okay, so we got the equation. We're going to have our upper bound. We're going to have our current value. And we need to say yes or no. It can be mathed. Can be mathed. Help. It'll take the equation, it'll take the upper bound, and then the value. Initially, we're going to start at 0. And what we're going to do is we are going to figure out how we're going to add things together. So to go through this again, if I have 10 and 19, what I want to do is I want to try 10 plus 19. Does that equal, like the left, does that equal 190? And then I want to say, okay, does 10 times 19 equal 190? And if I get to the end, basically if I get to this and I haven't found yes to this, so it'll be like this, so it'll be like false, keep going. And then it'll say true. And then you can stop. But if the numbers were like 18, it would be false, keep going. And then it would be like false. Keep going. And then this edge case would get hit because there would be like, we'd basically hit this first branch. So that's the vibe. So I think the shift left and shift right is going to be like how this works. Whew. Shift right. So I think the shift right stuff will work. So this is why the way I'm doing this is so stupid, because this is the most confusing thing I could ever use my words to describe. Like, what I'm saying is insane. I'm basically starting with a binary string. Let's start with a more complicated one. Let's start with this. All right. So if this is what we start with, what I'm doing is I'm saying, all right, the first time can be mathed help gets called, we are saying the number that's coming in is the equivalent of this. And so what I want to do is I want to loop through, right? So you got the 9, 7, 18, 13. What I want to try to do is say, if this is odd, it's going to be 9 plus. Or if this is a 0, it's going to be plus. And then I shift it over. So by shifting it over, I then chomp the next thing. I'm like, okay, if that's a 0, this is a plus. And I do the exact same thing until we run out of numbers. All right, so there's going to be another little loop going on in here, and it's going to keep looking at this bit. And if it's a 0, it is going to do a plus. And if it's not a 0, it's going to do whatever. And it's going to keep doing this. And so the whole time, I'm going to be keeping track of like a total. So initially, my total is, it's going to start at 9. And then because I chomped off and I said let's do an add, we're going to add the next number. It'll do a 16. And then I chomp off, and then I do the next number. It'll do 16 plus 18. It'll give me 34. Okay. And then it'll do one more chomp off, and it'll do that. And it'll get to the end of the list. So we're basically going to be folding through. This is going to be a list fold left. We're going to be working through the equation parts. We're going to apply operation. And then what we need to do is we need to keep track of like the state of the initial state. So the initial state is going to be, we're going to say else case equation.parts. If it's empty, we're just going to say false. There's no numbers that can do this. But if it has the first and the rest, what we're going to do is we're going to say the result, we're going to say the output equals whatever the first is. That's us saying grab the first number, 9, and put it here. And then the mask is going to be equal to the value that's coming in. And we're basically just going to do this. And so all we have to implement now is we have to say if operation dot output equals equation dot total, is that what, or answer? So if we found a match, then we return true and we're good. Otherwise, we keep going. And the way we keep going is we basically just recurse. We say do this, can be mathed help. It's still going to be the same equation. That's not going to change. The upper bound is not going to change. But what will change is the value is going to be incremented by 1, and that is going to allow us to continue simulating through the binary space, because I've decided to make this a binary problem. And I'm going to make a type here for operation. You can call it operation if you want. That makes sense. Type alias operation is going to equal. You take the output, take the mask. And then the output is going to be kind of the accumulated int, and then the mask is going to be int. We need the mask in our fold state as we're doing like the operations, as we're applying these, but we don't need, so apply operation is going to take in an equation part one at a time. It's going to take in the existing operation and return the new operation. So this is going to be like the next number in our list, like this, like the next part in our list. The operation, I'm just going to call it that. This should return false for everything in 0. So our code's coding. This is actually the logic we want, but we want to kind of run this simulation with our mask. So what I'm going to do is I'm going to say if, this is the fun part, we're going to say if the operation say is odd, basically, is add, is if the operation mod by 2, if that equals 0. So I'm going to say mod by 2, the mask equals 0. So is add, we're going to add if last bit is 1. Oops. So I'm going to say let in, if we're adding, then what we want to do is say the output for adding. Then we want to take the next part and add it to the output. So we're going to say take the operation's current output. We're kind of like building this up as we go, and we're going to add it. We're going to use the add operator to add that to the next part. Otherwise, we are going to multiply it. Oh, sorry, this is if the last bit is 0. So if it's even, we're going to do 0. But then the big return thing that we're going to do is we're going to say the mask needs to get bitwise shifted. So if I shift 32 by 1, it's basically going to, yeah, it's going to chomp off the right side. So this is it's like a math thing that we do. So when we shift right, what we do is we kind of just slide the numbers over. So we're going to slide over our binary numbers, and then I think this will work. Bitwise shift right by 1, and we're going to take the existing mask. And then for our output, we are going to do the new output. 0. Okay, let's see how we did. And then I'm going to say output here. I'm going to say mask here. Deploy operation getting called? Should be. Can be mathed. Help. Can be mathed. Oh, I'm not even calling this, am I? What the heck? Okay, so let's just try this with. This is going to be our puzzle input. Puzzle input. It's going to be that. Solve problem. I'm going to give it a puzzle input. So what I want to do is I want to just work my way up here. So if I have 190 colon space 1019, what do I get? Okay. 0, the output is 20. Oh no, did I do rest? That's the issue. Okay, there's the 190. Crap. Okay, that was it. I was adding 10 to itself, so everything was wrong. Sorry about that. All right, solve problem. 3749. 3749. What a heap of garbage that I just described. All right, this is crazy. Oh, this is wild. All right. Yeah. Okay. Yep, we did that. That was how we did it. Isn't that insane? Okay, let's get the debug log output out of here. That's just going to slow down our program. Format this. Compile this. Format this. Okay, whatever. Format this. Compile this. Save this. Okay, well, that is potentially part 1. We did it with binary. Pretty crazy. Let's try it with our puzzle input. So I think this is it here. So I'm going to scroll up. We are going to see if this works. That's a big boy. 4998764. Let's see if. Holy moly. All right, that was it. So just use binary, guys. Get good, you know? That's all I have to say. That was crazy. All right, let's see what's up. Concatenation. A new operation. Wow. Okay, so there's a new operator. So this is why I said bitwise was risky. Because now there are not 2 possibilities per bit. There are 3 possibilities that we need to go through. Crazy. All right. All right, let's see if the list.extra is going to save our butts. This is our only hope. Otherwise, I got to do... The thing that I don't like about permutations is that this just shuffles up the distinct numbers. What I need is I need something horrible. I need, like, give me a length. I need to, like, a list cycle. No, that's not it. But it's like that. It's like, that's the thing. Split at, groups of, greedy groups of, get at, remove at, cycle. I don't like it. Okay, I don't think this is gonna help us, but the same logic that we did still applies. The difference is it's not bitwise anymore. So maybe there's a trinary shift left. Okay, we don't have to switch it to trinary. I think we just need to shift by 2. I think if we shift by 2, we can still do all the same stuff. But 1 bit is not enough information to decide plus, star, or concat. So what I need to do is I need to say... I don't know why I'm still doing this in binary, but I am. So what we're going to do is we're going to say that plus is the equivalent of 0, 0, star is the equivalent of 0, 1, and concat, I'm just going to call it C here, is the equivalent of 1, 0. Oops. So what we want to do is this mod by 2 is add is no bueno. What we want to do is we want to say is if we take the mask, so this should still give us the same, hold on, this gives us the same answer, right? If we compile, get 3749. I'm going to change this code so that we still get 3749. Oops, I should save this actually. Well, we already saved it. I'm just going to name this before I forget. Day 7, part 1. Cut this, format this, compile this, save this, paste this, copy this. Now that it says part 1, we'll do this. Go to this, do that, save it. I do it all for you. You know, I do it all for you because I care about my viewers. All right, so what we're gonna do is we are gonna modify this so it still spits out 3749. We're still gonna get the right answer, but isAdd is going to use different logic. So I'm gonna get rid, I'm not gonna get rid of isAdd. What we're gonna do is we're gonna take the mask, and rather than saying is mod 2 0, which is a clever way of saying like, is this bit 0? What we're gonna do is we're gonna do a bitwise dot, what was it, bitwise. We're gonna do a bitwise and with like the add value. So I'm just gonna say add equals 0 times equals 1 and cat equals, it's gonna be 2. I don't know why the syntax highlighting got crazy, but this is the idea. So these are our values. So what I'm going to do is I'm going to say is operation, if you give me some type of op mask, like add, times, or concat, I'm going to say it is the operation if when you and the mask with the end of the thing, you get it back. So is operation add. Hot mask. Call this plus. It's not. And the op mask. What do I do differently here? If 0 ended with bitwise and. I need a new LE. Well, I don't need a new LE. I'll just do it in here. But bitwise and I go 0, 0, I should get 0. I get 0, 1, I should get, I should also get 0. So this isn't really what I want. I don't want and, I want XOR. Obviously, how do I get the left 2 bits? So if I can get this to spit out 3729, I think I can modify my problem. So are they different? So this should return 0. This should return 2. Okay, great. So they're the same if the last 2 bits of my mask. How do I get the last 2 bits of my mask? I gotta AND it with a bit mask. I need a bit mask. I gotta AND it with 3. Okay, I got this. We're gonna take the mask. This is crazy binary stuff. We're gonna take the mask. We're gonna AND it with 3 because 3 represents binary 1, 1. So we're gonna say take all of this huge string of numbers and basically make it so we only have this. And then tell me if bitwise, if I XOR it with this operation mask. So I say like, give me all the bits that are different. If that equals 0, that means there are no bits that are different, which means that the last 2 bits match the operation I'm supposed to do. So 3 here because I want to AND it with 1. Okay, so let me try this again. 3749. Okay. So now I made it so that we can provide a bit mask. I'm gonna move I'm gonna move some stuff. To upper bound needs to be rethought, because to upper bound, it's now the equation parts. But it's gonna be twice as long. Bits for operation. Okay, so because we need 2 bits to represent 3 operations, that's that. The bit mask is going to be 3. Because this represents this. So if I need 1 bit for my operation and 1 for the bit mask, that gets me my 379. But if I start to represent 2 bits, 3 bits, I need to get this to also say 379. And the way I'm going to do that is by shifting bits for operation. Okay, we just did it. So, okay, so this is the exact same answer, but we added another bit here. So this, actually the bit mask can be calculated by 2 to the power of the bits for the operation minus 1. Okay, we're cooking. Okay, so this is our mapping of, I'm happy with this. All right, 0, 0, 0, 1, 1, 0. The bits we need for the operation are 2. See, I need like 2 bits for each operation. The bit mask is what do I multiply to just get that last slice. And so what I can do here is I can say else if the operation is times, then we do times. Otherwise, we're going to do this whole concat thing. So we're almost there. We're not quite there. But this should just return like something's crazy, like 9,000 or 90,000. This should still work. Okay, this still works because we're hitting this the second time around. So what we're going to do is we are going to make this concat. So plus is going to do this, times is going to do this. But now I need to apply my operation on strings too. So the part I'm going to save right here, compile. Okay, what I need to do is I need each part to be a string. And in order to make that work, I need to change what equation.parts is. So we have to go into equation, and we have to say that the parts aren't integers, they're strings. So equation is defined somewhere. So this is a list of string components. I'm going to hit compile. I'm going to let the compiler guide me through everything. So what we're trying to do is on 77, we are going to say the first value, it should be numberable, string dot, we'll just say output, the initial output here needs to be a number. So string dot, take the first string, this is a string now, string dot to int, and maybe dot with default 0. We're going to assume that our input's always valid, so all these made with defaults will be okay. We can't add numbers, we can't add strings to numbers. So what we're going to do is we are going to say, take the next part, string dot to int, we dot map it. We're going to use some fancy Elm syntax. We're going to add it. And then if we fail to do any type of operation, we're going to do that. So we're going to do like, this is going to be like int operation. int operation helper that takes a function, basically just runs that function on those two numbers. So this is a function that goes from int to int, and its goal is to return an integer. Cool. Output. Oops, sorry. Takes in 3 integers. Oops. Where did that go? Okay, cool. And now we have a maybe int strings. We just don't want to run this filter map. So I'm going to look for filter map string to int. I know you're in here. I know you're in here. Oh, there you are. It looks like I can't search. That's okay. We still get the same answer, which means that that refactor worked. What we want to do here, though, is the operation output also needs to be a string. Actually, I don't think it does. I think the output can be, we're going to concatenate. Yeah, we're going to turn this to a string, we're going to squish them together, and then we're going to turn it back into an int. I think that's the vibe. So this is going to be concatenate. So if we take the current output, string dot from int, string dot join, that with the next part. Okay. Okay, I don't know how we actually put the concatenate up. I feel like I've lost the thread. But anyway, so we've got that. That is a thing. We're going to string dot to int. And then if that fails, no worries. We're just going to do that. Next part. Ooh, next part. Sorry, unit. Great. 4079. Okay. So this is the part that I needed to fix. What have I done? So I think number of operations is probably what we want. This should, number of operations. So this is 2. This is the part where I'm realizing that I'm missing something. Yeah, this doesn't make any sense. Ew, what am I doing? All right, let's start with, let's just do this real quick. 190. Go through that space. Ever concat? What was the one that got brought over? 156, 15, 6. Just curious. Seems to work. Oh, 4097. Is that the answer? Oh, sorry. Let me go back. Yeah, I'm not sure how. Okay, I think what I need to do is I need to handle the no op case. So else if is operation hat, then do this. What happens if I get 1, 1? I don't know. I guess I'll do that. Just leave it as is. Is that right? How am I doing with this binary stuff? Where did I do this in binary? Why am I a psychopath? We just ignore it, right? Yeah, we just shift it. Yeah, that seems right. Okay, cat. Yeah. So that's that. That's that. That's that. To upper bound. Upper bound. The bits for the operation. Okay, I just want to slow down and see what. So I'm summing these up. Let me not sum them up. So it's claiming that these are good. Cat 190. Where do these numbers come from? 90, 32, 292. So it's saying 156 can be concatenated, and 192 be concatenated. I just feel like the no-op should work. What's the mask? Yeah, the mask is. I'm gonna switch this to floats and see if it just fixes it. How many gaps there are? 0. I'm surprised that this isn't working. I mean, I'm not surprised. I'm confused about how any of my code works, but. Oops. 4097, but we want to get what? Because 7290 isn't working. So I want to take a look at this. So it's saying if we do 6 times 8, 486 times 15. Is that what it's saying? 486 times 15? 486 times 15. Okay, so that's how it's doing it. So I want to debug all of these. I just want to see what this is doing. Okay. And then I want to see first operation. Oops. All right. Debug.log. All right, let's see this log. So let's hop over here and let's grab that snippet. So this is, I think, adding them all up. Okay, so this is the input. So if I have 720, 6, 8, 6, 15. This is using rest, right? The rest, the first, the rest. Okay, great. Good, good, good. Okay, so what I want to do is I want to treat, every time I see this, this, and this, I treat it the same. So I think it has to do with my fourth bit. I think that's like the no op that's like here. I think this is what's causing the issues, but we'll see. So what I want to do is I want to think through this 35. So the 35, I think, is from adding all these up, because the binary that should be coming in at first is 0, 0, 0, 0, 0, 0. So that should say add, add, add. Oh, I'm adding 1 each time. Maybe I should add... What am I doing each time? I'm adding 1? I wonder if changing this can fix it. Sorry, I'm like half debugging and I'm half not. I can say number of operations equals 3. I'm going to say if I were to add 1 to the value, and it was going to add in a 1, 1, if it was going to end in a 1, 1, that would mean a bitwise and with 3 would equal 3, and I don't want that. No, okay, sorry. Sorry. God, what am I doing? Okay, let me not do that. I don't know why that doesn't fix it, but I also don't know how this works. Else. Okie dokie. Okay, I'm just gonna undo that. Sorry. Okay, compile. Okay, we're back. Output logs. Okay, so I just want to make sure that this is working the way I think it is. So I see 3 zeros. I translate zeros to pluses. So I see plus, plus, plus. So I should do 6 plus 8 plus 6 plus 15. Calculator says, what the heck? What the hell is this calculator? It's crazy calculator. Equals this. 35. All right, let's keep going. So that makes sense. The next time it comes in, this gets bumped up. So six plus 6 plus 6, that times 15. This is what I would not expect. Ooh, Operation Mask. Yeah, no, this isn't good. Like, this else isn't good. It's like I shouldn't be putting in invalid instructions. All right, here's what I do want to do though. I think I want to restore what I had here, which was like, oops, sorry, this is crazy. Else if, this is just the dumbest way. It was the most, like, the cutest thing I could have done that just immediately backfired. Else if I add 1, yeah, I add 1, and it was 3. It says equals 3. This is incredibly hard coded. Skip it. Because I don't want anything that ends in 3. So what I really want to do here is I just want to log the value. So it should go 0, 1, 2, 4, 5, 6. Yeah, it should skip all the ones that add in 3. So I like this better. I think this is on track to solve the problem. And then what I want to do is I want to kind of translate these. Let me make a little helper that takes the values and just prints out what these should be. Because I think so weird. Okay. We're doing so good until we weren't. So this should never happen. Let's just make sure this never gets hit. Crash. It is crashing. This isn't doing what I expect at all. Doing a shift right by 2 each time. Oh, yeah, that makes sense. Okay, well, that's dumb. All right, so I gotta stop doing this weird binary thing. Why don't I just make all these lists, huh? How would I do it? How would I do this in a normal human way? I guess I would just kind of not be a psycho. I'm trying to think of how to do it. I think I can just, if I can figure this out, I think we're good. I think it'll work, and I don't have to refactor the entire universe. All right, to next value, take an int. And this is gonna make sure that I never have OB11 in a segment. So if I get OB000110, that should be okay. But if the binary, any of these, I'm just gonna increment one. That's okay. Oops, so this would be like that. So I don't want to increment by one each time. Do I? Because that might take forever. Might be hilarious. Whatever, let's just do it the dumb way. Number. If a value this is crazy. I absolutely did this the dumbest way. It was so cool. It was so trendy. But then what was the cost, you know? Oh yeah, there's half written code up here. So if is operation 3, then the next value. If this, so if this ends in this, then it's, we need to just move on completely. This is crazy. All right. This, yeah, well. The next value help. Num is the original, and then num is the, yeah. This is crazy code, you guys. I don't think this is even informative. This is just like, I'm technically completing the element of code. This is the original. This is the mask. So if text value help +1, and then we reset the mask. So this is like, move on. Otherwise, test is the mask 0. So that's our base case if we've run out of bits to chomp. Otherwise, I'm just kind of like working my way through and just like checking this, and then I want to do a bit shift right. Original, so that's the number we're testing, and then I want to do bitwise shift right by bits per operation. It should be 2. I'm just gonna hard code 2. We're hard coding 3. We're hard coding 2. Mask. infinite loop. Oh man, all right. This was so easy. This was such an easy problem. And then I decided to do binary. But I guess if I really believed it was easy, I wouldn't have done binary. That's the bug. Okay, that's the bug. So we shouldn't see any more crashes. Great. 0, 1, 2, 4, 5, 6, 8, 9, 10, 16. The upper bound wrong? The upper bound wrong? So if I have 4, there's 3, that's 8, that should be 8, 16. I feel like that wouldn't be broken all of a sudden, right? Ooh, okay, output. What blocks? Run is 15. Run is 15. That's not scanning enough. I think that was it. I think that was the issue. Oh. Okay, there were a few bugs, so we did need to fix that. Okay, what I was doing was I wasn't doubling the total number of bits. I was doubling. I was adding one more bit. I needed to be adding. If there were 3 things, I basically needed to add a bit in front of everything instead of just. It was basically going from 3 to 4 instead of from 3 to 6, and so it wasn't scanning through the whole space. Yeah, this seems like it's gonna really chug along as we get into bigger numbers, but I don't know. I don't think it will. I think we'll be okay. Cool. So this should never get hit. But if it does, it should crash. So that should never get hit. All right, I'm gonna save this. This is part 2. Let's see if this works. If it did, we made it a week, which is pretty sick. But the binary choice, wouldn't do it again. Would not do it again. It's gonna take a while because we're gonna be adding a lot of numbers. Big numbers, folks. We did it. Thank you for watching me do this for a week straight. We have 14 stars. I might continue doing these casually, but it's 2024. It's been a week. It's been a week of Elm. We did it. I am sorry about doing binary on the very last day. That was psychotic behavior. But I'm glad we did it. I'm glad we got it to work, and I'm glad I know how bit shifting works. So check out the Bitwise Elm package if you ever want to do something horribly wrong. And I'll catch you guys. Have a wonderful holiday. Merry Christmas, Happy Hanukkah, whatever you got going on. And then, yeah, Happy New Year. I'll catch you later.